Hi, Vera Mace here from the Learning Commons. Sorry we had a little bit of technical difficulties, so we're starting a few minutes late. So let's go ahead and talk about radicals. One of the things we're going to do is talk about technology, so we're all calling the same thing. And then we're going to do some addition, subtraction, some multiplying, and then deal with a little bit of rationalizing the bottoms. All right, so it's really important that we all know the same things and call the same things the same, so that we know what we're talking about. It's like learning a brand new language. Most of us start off being familiar with square roots because we've seen them in junior high or high school or something like that. So for a long time, you think that's the only kind of radical there is. And then you start learning about cube roots and fourth roots and fifth roots. So you're like, there's more out there. So that index number, whether it's a third or fourth or fifth, it's going to be really important to us. The inside is called a radicand. That's going to be important to us too. And then the whole thing is called a radical. All right, some of the ones I think you probably have seen, square root of 4. Most of us know 2. There might be some others you're thinking right off the top of that. 9, most of us know 3 times 3. So you're noticing pairs. It's when their factors match. 25, same thing, 5 times 5. All right, so let's look at now that some that are not. And the only way I can break them down is to kind of tell you a little bit of story. It's a fun way to kind of remember radicals, and it works whether it's a fifth root, a fourth root, a cube root, whatever. So you want to think of radicals as being a jail. Nobody wants to go in, but everybody wants to get back out. So if it's a square root jail, that means there's these guys, it's so bad in there, they're trying to get out. The wall's tall enough, though, it takes 2 to get over. So what they decide, okay, you got a family, you need to get out, I'll stay and hold you, help you get over so you escape. That one gets shot. Sorry. And then it keeps going like that until you don't have any buddies to help you climb the wall. You're just going to stay in the radical jail. So let me show you how that applies to numbers. All right, so if you have a square root of 8, there's no factors of 8 that are the same. So we're going to break our numbers down. And one of the best ways we can do with smaller numbers is to start by going to prime factors. And you can do any of the factors of 8 that you know. Any place you start, you're going to end up with the same answer. So square root of 8 is 1, 2, 3 2's. Remember I said this is a square root jail, so we're looking for 2. There's a little invisible 2 as an index on the square root. We don't write it because we kind of assume that's what's there unless I put something else. Since it's a square root jail, these 2 get together, they work it out. One survives, the other dies. This guy doesn't have any buddies, so he stays inside by himself. Let's look at another example. 54. 54. It's an even number, so 2 and 27. 2 is a nice prime number, so I know that's going to go underneath. 27 is 9 and 3. 3 is a nice prime number. 9 factors into 3 and 3. So now we look inside our square root jail. We're looking for pairs. I see a pair right here. That's the only pair I see. So these guys work it out. One climbs the wall, the other one dies. And then we got 2 times 3, so it leaves us a 6 that's left on the inside. So you break it out, find your pairs, bring out a representative from each pair to the front, and then multiply the others back together on the inside. And this will work whether you have letters or numbers. So I'm going to do a short one, and then I'm going to give you a shortcut for the numbers, or the letters rather. So x to the 5th. That means there's 5 of those x's inside of there. If I start looking for pairs, well, here's a pair, so they're going to send an x out front. Here's another pair, so they're going to send an x out front. But this guy doesn't have enough buddies, so he's going to stay inside. So x times x gives us with an x squared and 1 on the inside. Now, as the numbers start to get bigger and bigger and bigger, you're like, she's crazy if I think I'm going to write x out 100 times and start circling. So there's definitely a shorter way to think about it. These numbers aren't huge, but I thought they'd give us a good demonstration until we tried the larger numbers. So remember, we're looking for pairs. So you ask yourself, how many times does 2 go into 4? The exponent on the x's. Well, 2 goes into 4 2 times with no leftovers. So there would have been 2 pairs of x's inside this if I were to write them all out and group it. All right, 2 goes into 5 for the y's. Well, 2 goes into 5 twice, and it has a remainder of 1. So one of the y's would have had to stay inside. 2 goes into 7 3 times, just space that out, and has a remainder of 1. So your final answer, x squared, y squared, z cubed, and a y and a z had to stay on the inside. So you don't have to write them all out. It's good with numbers, especially until you get used to doing it, looking for pairs or cubes or whatever your index is. So let's look at this last one. Cube root this time. So we're looking for 3 at a time, or we're going to be dividing 3 into each of the exponents. So the x's, 3 goes into 100 33 times with 1 left over. You sure wouldn't want to divide 100 x's. 3 goes into 25 8 times with 1 left over. 3 goes into 27, nice and even, so there are no z's left over to stay on the inside. And this trick that we're doing here works no matter whether it's a cube root, 4th root, 5th root, doesn't matter. All right, so that's simplifying them. Now we want to be able to add things together. It's really important that certain things match so that you can add them together. It's kind of like adding an apple to an apple or an apple to a pear. Apples to apples we can add. Apples to pears, all we have is fruit salad. So they just stay the same. So if we look at them, the index and the radicand has to match. So if you look at this example, the index is 3. And the radicand, the number inside the radical is 7 on both of them. So this is like saying I have 2 apples plus 4 apples. Well, you would have 6, and it would still be apples. So that part doesn't change. So once you make sure they're both the same radical, then all you're dealing is with the coefficients using your positive and negative rules that you guys have been using for a long time. Not going to let me read it down. So 2 square roots of 7 plus 4 cube roots of 7. So we have to verify, does the index match? This is a square root or a 2, and this is a 3. So I cannot combine those. I just rewrite them exactly the same and move on. All right. The next one, both cube roots, so that's feeling pretty good. But this one has a 16 on the inside, and this one has a 2. So at first glance, you say, no, never mind. But I have a sneaky suspicion that if we break that 16 down, we might have something that's similar. So let's look at 2 cube roots of 16. If we factor 16, let's see, 4 and 4, or 2, 2, 2, and 2. 1, 2, 3, 4. So it's a cube root. So I'm looking for a pair group of 3. There's one group of 3. There was already a 2 out in front. So this 2 comes to join it. And it leaves behind a cube root of 2. Actually, this one then simplified to 4 cube roots of 2. And the other one was 4 cube roots of 2. So now the index matches and the radicand matches. So we have cube roots of 2. How many do we have? 4 plus 4. And this would work whether it's addition or subtraction. See if your radicals can be simplified, because sometimes they're hiding where it doesn't look the same, but they really are. All right, let me skip to that one. Okay, multiplying radicals. Again, it's really important where the numbers live. So the radicand can be multiplied by the radicand. Remember we use the analogy like of a jail? So if they're in jail, they can talk to each other. If they're outside the jail, they're not going to come back inside. All right, so let me give you an example. This is something you're used to doing lots and lots of, is distributing. Oops. Multiply first times first, first times other. So you've got 2 square roots of 3 that are going to get multiplied by a square root of 3, plus 2 square roots of 3 that are going to get multiplied by 3 square roots of 6. Well, the square root of 3 and the square root of 3 are both inside the radical, so they can get multiplied together. 2 in front, square root of 9. Over here, I've got a 2 times a 3 with the coefficients. Inside the radicals, I've got 3 times 6, so I have an 18. And then before I leave this radical, I have to see, can I simplify? Well, square root of 9 we talked about was actually just a whole number 3. And then 18, is it 2 and 9, 3 and 3. So there's a pair of 3s to come out and join the 6. And the 2 stays inside because he didn't have enough bays. So I have 6 plus 6 times 3. Now, because the 6 doesn't have a radical, I can't combine the 6 and the 18 because it's a lot like, let me give you an example from what you've been working with before. If you do 6 plus 18x, these are not like terms, so you can't combine them. If they both had a square root of 2, I could combine them. All right, let's look at the other example. I'm multiplying, so I can multiply the coefficients, and I can multiply what's inside the radical. All right, does x, y simplify? I don't know what x is, I don't know what y is, so I don't know if these are nice, pretty numbers or if they're just 1 and 2 or anything. So that would be my final answer. That one actually looked kind of weird, but it would end up being a simple one to do. All right, so multiplying, multiply the outsides, multiply the insides, and then simplify and see if there's any like terms. All right, one last thing that we like to do. We don't really talk about dividing with radicals, but somewhere way, way, way back, they decided that you are not allowed to leave a radical on bottom. So they came up with a process that's called rationalizing. And it's a way to get the radical off the bottom. So we know that radicals are looking, square roots are looking for 2. So if there was another 7 here, I would have a pair of 7s and it could come out. But we know if we do it to the bottom of a fraction, we have to do it to the top. So on bottom, I have square root of 49. Square root of 49. Most of us know, or you could do it on your calculator. So I've got a 7 on bottom. On top, 3 times square root of 7. The 3 is not inside the radical, so it's going to stay on the outside. Now, the last thing you do with every fraction is look to see if it reduces. You never can go back inside the radical, but you look at the coefficient in front. 3 and 7 don't reduce each other, so that's my final answer. One more. I've got the 2 on bottom of a fraction. We're good. We're fine. It's this square root of 5 that can't stay there. So we're going to multiply by the same radical, top and bottom. Multiply the top, I get 5 square roots of 5. On the bottom, I've got a 2. 5 times 5 gives me square root of 25. If I simplify the bottom, the top, square root of 25 is 5. So 2 times, oops, looking ahead. So I end up with a 10 on bottom, 5 square roots of 5 over 10. I mentioned a while ago, every fraction that you have, the last thing you look for is there anything on top and bottom that reduces? So Bob, is there anything reducing?
Sure.
Yeah, we have something on the same from top to bottom. So 5 goes into 5 one time, and it goes into 10 two times. So your final answer is going to be square root of 5 over 2. So this is kind of a brief run through on adding and subtracting, multiplying, and rationalizing. As I mentioned earlier in other videos, if you want to come in, get some help, we'd love to help you. There's some really good handouts on our virtual commons on working with radicals. So I look forward to seeing you guys. Take care.
All righty.
I wonder how the sound works back here.
I don't know. We'll find out.